Okay, let's get started. So last time, if we recall, we covered how machine learning works. So that was pretty cool. Today we will start talking about some practical considerations, and then we'll start introducing probability, which will allow us to do a few new algorithms, which will be fun. But I want to start by revisiting regularization and covering it in a bit more depth than we rushed through at the very beginning of this course. And to motivate regularization, I want to talk about a few of the times and a few of the situations that can lead to overfitting. So one type of situation that could lead to overfitting is using too many inputs. So let's look at an example, and I'm going to use a non-health example. I'm going to try really hard in the next few classes to make all my examples outside of health. And so for this one, I'm going to go back to the sentiment analysis classification example we were doing. And so we're going to look at two features. So one feature will be the length of the sentence. This is a reasonable feature. And another feature, which we talked about before, is the number of curse words. And let's say our data look like this. Doesn't matter exactly how you draw it. This is just an illustrative example. Let's say the data are like this. And let's say we have a model that is pretty powerful and therefore learns a decision boundary like so. So everything in that purple area is classified. Oh, let me label these. So in this example, we'll say that the blue X's are positive sentiment, which makes sense. They have less curse words. And the red are sentiment. So using this decision boundary, we could classify a new point. So let's say our new point fell here. Then this would be falsely classified as negative sentiment, even though probably a better decision boundary would have classified it as positive sentiment. Same for over here, so let's label that falsely classified as negative sentiment. So there and there. So because we considered the length of the sentence, which doesn't really have anything to do with the sentiment of the sentence, and because just randomly the positive sentiment examples in our training set happen to be mid-length, whereas the negative sentiment examples had all sorts of lengths, our model falsely learned that bias. So by including that input feature that was unnecessary, we are making worse predictions by continuing to predict with that feature. So that is one issue with using too many features, and regularization, which we'll talk about in more depth, but which we talked about before, is one way to reduce features, but we will talk about many other ways to reduce features in the future. So a second overfitting situation, so this was the first overfitting situation. The second one that we'll talk about is using...
Sorry, I have a question.
Yes.
I just want to clarify. So when you say using too many inputs, do you mean like too many inputs in each category, or just too many, categories in general?
So the categories are the outputs. So the inputs are the number of curse words and the length of the sentence.
Oh, so we're just considering two parameters.
Yeah.
Basically.
But it would have been better with just one in this case.
Oh,
Obviously, this is an illustrative example. In the real world, you have hundreds of inputs, and you might want to reduce it to 20. But in this illustrative example, it also is 2 is too many in this case. So second overfitting situation is using a too complex model. Is that correct grammatically?
Too complex of a model.
Too complex, right. So much to write. Too complex of a model. And we're just going to go back to that same plot. Just going to draw it really fast and kind of, it's not going to be exactly the same, but roughly similar. Doesn't really matter where the red circles go. Okay, so if we used a simpler model, let's say logistic regression, which is limited to finding linearly separating boundaries, then we might learn a line that kind of goes this way or a line that kind of goes this way, but we're kind of constrained to separating the data with a line. And so whether the line has a negative slope or if we had it with a positive slope instead, as long as it's separating the points, it would have done better. So let's label this a simpler model. Or is it more simple? Anyways, would have done better. Like that. And this is really important because modern machine learning, which we haven't gotten to yet, but like deep learning, which we'll cover extensively in the second half of this class. So modern machine learning, i.e. deep learning, which we all know what that is, even though we haven't learned about it yet because it's so popular, can learn any function. So this is just an illustrative example again, but let's say we had data that were spread out like this. Drawing a smiley face, but for an educational purpose. So if the data were spread out like so, let me draw some other non-blue X's. Way too complicated for logistic regression. Imagine the equation for that separating line, or boundary rather, and the boundary had to kind of be like so. Let's say there's a random boundary in there too. It's even hard for me to figure out as crazy boundaries. Like that's probably a pretty complex function, right? But it is easy peasy for deep learning. This would be no problem. So deep learning models could really learn any function. You could have a function that is like tangent to the -1 of pi divided by et cetera, and you could write out the function in several book volumes that fill up 28 libraries, and that would be easy for deep learning if it was a large enough model. So we're in a state in machine learning where we have models that can learn anything we want, but sometimes they're too good and we don't have data sets that are big enough to accommodate those models. So overfitting is natural when we have models that can learn anything.
Can you tell if you're using how do you tell if you're using too many inputs versus too complex of a model?
That's a good question. We'll get there a little bit later. Yes?
When you say a simpler model, like, for example, in this case, how would you make the model simpler?
No, this is a simpler model. I'm pointing to a simpler model.
Okay. Oh, okay, sorry.
Let me clarify that. This is the simpler model versus this model up above on the same data. Let's say more complex model. So regularization is one tool that we have in our toolkit to automatically simplify a model. So it's not learning a complex decision boundary like that, and rather learning a simpler boundary like that. So let's write this a little bit more formally now, but that was the motivation. So regularization helps us constrain the model basically from doing so well that it fails to generalize. So I had shown you in the past L1 and L2 regularization. Let's revisit those definitions just so we can remember them and then build upon them. So L1 regularization is where we add this hyperparameter times the sum over our model parameters of the absolute value of the model weights and similarly L2 regularization is where we add that lambda hyperparameter times the sum of our parameters of the square of the weights to the loss function. So for example, our loss function might be minimize, and I think when I wrote this out, I wrote the whole equation for mean squared error. I'm just going to write MSE for short, just so you're not confused about that, plus this regularization term. And that would be now our entire loss function. With regularization. And you could think of this intuitively as you want to minimize the error. That's always good, right? You want the error between what your model predicts and what the actual value is to be as low as possible. So minimize the mean squared error in the case of linear regression. But we don't want to have our weights of our model, so the m's and the b's in linear regression or our parameters be too large. So therefore, we add to this equation we're trying to minimize using gradient descent, we add the weights of our model up so that the lowest loss is not necessarily going to be the loss with the lowest mean squared error from before, because we're adding the weights of the model. So the more weights our model has, does this make more sense in terms of gradient descent now that we've covered gradient descent? Okay, yeah, that's what I thought. But let's dig a little bit deeper now into what happens with L1 and L2 regularization and why we would use one versus the other. So L1 regularization has the nice property that it leads to feature selection, which is a vocab word meaning reducing the number of input features in our model. Let me write feature a little bit more clearly because it's an important term. Leads to feature selection, which is where we want to remove inputs from our model. Where we remove inputs from the model. And I think the only way to really see this is to draw it out pictorially to see why this may happen. So I'm going to draw a plot with theta 0 and theta 1. These are just two of the parameters of the model. And let's say that our minimum is over here. So this is the choice of theta 0 and theta 1, choice of model parameters that leads to the lowest loss function. So this is our the place where we have lowest loss using mean squared error alone. And now let's say that if we start regularizing in a certain direction, we have different possibilities for combinations of theta 0 and theta 1 that will lead to a particular minimum loss value. But what the L1 and L2 constraints do is basically require that theta 0 and theta 1 are as low as possible. So what I'm drawing here, let me redraw this. I meant to draw a diamond, but that's not.
Sorry, can you repeat that? You say L2 for you to be as low as possible?
Sorry?
L2 makes them as low as possible?
Both. We'll see that. We'll look at the difference between L2 and L1 and how they make them low in different ways.
Sorry, could you say what the blue stuff is again?
So, let me label this. So this point is the value of theta 0 and theta 1 with lowest mean square error. Don't worry about these circles yet. So this red diamond is showing us combinations of, this will all start to make sense in a second, theta 0 and theta 1, which form a particular value for the regularization term. So for example, the absolute value of theta 0 plus absolute value of theta 1 equals 1. So basically, as we increase our regularization, this diamond might expand or contract. But if we're saying that we want, so when we're let me label this. When we're minimizing this entire loss function where this is the regularization. Super clear. We're jointly optimizing these two terms. So we're trying to minimize this entire function, and we want we want both of these terms to be as low as possible, but if we make the weights too low, then the mean square error will suddenly will be really high because we don't have a good predictor. So when we have these two terms, we're looking for the optimal balance between minimizing error and having low model weights. Does that kind of make sense from an intuitive standpoint? So basically, what happens in L1 regularization is that, well, actually, let me draw L2 as well. So I'm going to draw the same thing, but for L2. And in that case, we kind of have a circle, because let's say that if we're drawing all possibilities of where theta 0 plus theta 1, absolute value of those, equal 1, that would form a diamond. And you can say, okay, like when theta 0 is 0 and theta 1 is 1, that would be the tip of the diamond. The top tip of the diamond. When theta 0 is 1 and theta 1 is 0, that would be this right corner of the diamond, and there's a linear trade-off between the two, versus when it's L2 regularization, then you're minimizing theta 1 squared plus theta 2 squared equals 1. That forms a circle, because x squared plus y squared equals 1 is the equation of a circle. So that's why we're drawing this. And so it doesn't have to equal 1. I'm just drawing, it's all the places where the sum has the same value, where the regularization term has the same value. And so what happens is if we start drawing, if we start expanding, going away from our local minimum, the first place where we intersect with the L2 boundary is on this certain point of the circle, where but by contrast for L1, the first place where they intersect tends to be right at these corners. You could kind of see that visually, where the value of one of the parameters is 0 and the other value is not 0. And so just conceptually, that's why L1 tends to lead to feature selection and L2 doesn't. Don't worry, you're not going to be tested on this. I'm just trying to give you some intuition on when you're doing joint optimization, why you can expect L1 regularization to remove a feature, whereas L2 does not.
Is it intersecting both the L1 and L2 lines at that point?
So we're looking for we want to minimize the MSE, right? So we're looking for the first point of intersection. And the first point of intersection for L2 is on the circle. The first point of intersection for L1 is on that head of the diamond. So yes, technically that line for MSE that hits the head of the diamond also intersects the circle, but that's not the first point of intersection for L2. The first point is on the circle, or the closest point to our loss. Yeah.
Can you say again how L1 and L2 impact feature selection?
So L1 tends to lead to feature selection, and L2, which we haven't covered, tends to. So let's write. Did I write that out? Yeah. L1 leads to feature selection, whereas L2 leads to dampened or smaller model weights for all features. Again, this is the intuition as to why that's the case. So for example, in a feature selection, case, we might start off with just another example. Let's say we're classifying animals now. So x1 is maximum speed. x2 is number of letters in name of the pet. So we're classifying pets specifically. And pet dog. And this represents a pet turtle.
When you say that L1 and L2 leads to these different things, is it that first point of intersection?
Yes. Yeah, exactly. So, yeah, not so good, but after feature selection, removing x2, because number of letters in the name of the pet doesn't matter, we're left with a one-dimensional input space, so just x1. I don't think I've ever drawn for y'all a one-dimensional example, so let's just do that for fun. And so if we're just only plotting the one-dimensional value of the points, then we might learn a boundary like that, which is, first of all, much simpler, much more intuitive, but also potentially does a better job because it's not learning these arbitrary patterns in the data. So that's after, for example, running L1 regularization. And whereas in L2, so let's draw a smaller weights example. And let's draw a regression example, just to give you some variation. And just for fun, let's try to make it 5-dimensional. This is my best attempt at drawing a 5-dimensional feature space. Actually, 4-dimensional feature space, and then a 5th dimension for the predictor. And let's say, I don't know, let's say the data look like that. Whereas with no regularization, we might have learned that. No L2 with L2. We're not removing features, but we might have, we're not going to have a line necessarily because all the weights kind of go down, but it's not as drastic of an effect because the weight values have all gone down. So they're all kind of important, but they're not having as dramatic of an effect as before. So any questions on regularization in L2 versus L1?
So L2 minimizes the effect of the weights.
Yeah, so L2 tends to keep all your weights there, but just reduces them to really small values, whereas L1 tends to also reduce many of the weight values, but eliminates a bunch of the weights down to 0 or near 0 as well. And again, this is the intuition as to why.
So is the magnitude at which the weights are damped uniform for all of the weights, or does it vary?
It can vary. Anything?
The regularization, is it possible for sometimes regulation just to fail outright?
Yeah, I mean, you might need maybe all the inputs are super important, and maybe you want to have maybe you need a complex model, and in that case, regularization is making things worse. So it's kind of a trade-off between what model are you throwing at the problem. If you're throwing linear regression at it, probably you don't necessarily need to do L2 regularization, although it would be useful to do that as well, but it's not as important as, say, if you were doing a high-order polynomial regression where you're predicting your weights are theta 0 x to the 10th plus theta 1 x to the 9th. That could, if you're using that model, you can learn a much more complex model, and if you add regularization, you're making it easier for the model to eliminate some of those features, so that you don't need to use the x to the 10th term if you don't need it, for example.
But sometimes you really will need those terms, so it'll make it worse.
Yeah, so it's hard to know in advance, but it largely depends on the type of data you have. And that's a recurring theme in all machine learning. It's different methods work better for different types of data. It's one of the big lessons. Okay, well, if there's nothing else for regularization, let's go to a new topic, probability. So this is going to be the second math concept. So up to now, we've been doing everything with, at first, algebra, and then algebra and calculus. Now we're going to throw in probability into the mix. And if I recall correctly, everyone's already taken probability and statistics, so I can go fast through this. Okay, has anyone not? Okay, so we'll just make this a quick review then.
That's as if we've taken enough.
Okay, well, maybe in the middle then. And the motivation for covering probability is that many machine learning models are based on probabilities and output probabilities, and therefore probabilities are an important concept to learn. And we'll use probability for a few mathy things, either today or next time. Don't worry too much about the math, it's really just complete stuff. But then we'll use probability for a bunch of supervised learning models beyond logistic and linear regression. So it'll be the basis for, in particular, naive Bayes, which is the coding problem in homework 3, and decision trees, which is one of the writing problems in homework 3, and neural networks. We'll get there later. So just some notation. It's common convention to write probabilities as so. So this notation means the probability of event A, where event A might be, let's say you want to know the probability that you're going to hit a home run if you swing your bat. So event A would be hitting the home run. So let's say that your probability is 35%, which is pretty high. Then you would write P of hitting home run equals 0.35. We also have conditional probabilities, which are written like so. Probability of event A given event B. So probability of event A given event B. And one more notation, probability of not A is written with this symbol, probability of event A not occurring. So that's just some notation to get us started. There's a few basic rules which are supposed to be intuitive. They start off intuitive, but then they get kind of unintuitive. So starting with the intuitive ones, the sum of probabilities in an event space equals 1. Do y'all know what I mean when I say event space? Or should I review that?
Good to go.
Okay, cool. Any particular probability has to be between 0 and 1. So 1 means 100% probability, 0 means 0% probability. And another intuitive one, probability of event A not occurring is equal to 1 minus the probability of A occurring. And similarly, the probability of A occurring is 1 minus the probability of A not occurring. So all very intuitive so far. Getting slightly less intuitive, the probability of A or B is equal to the probability of A plus the probability of B if A and B are mutually exclusive. Mutually exclusive means that if A happens, then B does not happen. And the easy way to start intuiting behind these rules is to draw it out. So this rectangle represents the event space. This is all the possible events that can happen. This is A, and that is B. And so the probability of A or B happening is the area of this circle for A plus the area of the circle for B. Does that kind of make sense intuitively? You sum them up because out of the total amount of possibilities that you have, A and B is the amount of possibility for A plus the amount of possibility for B if there's no overlap, or in other words, if they're mutually exclusive. If they're not mutually exclusive, then probability of A or B equals probability of A plus the probability of B minus the probability of A and B. And we can intuit this by drawing it out. And now if they're not mutually exclusive, then this circle represents A, this represents B, the intersection is A and B. So A or B means that it's the entire area for circle A plus the entire circle for B, but we double counted the intersection in that sum, so we remove that intersection, which is A and B, and now we get the area of A and B without double counting any of the area. So you could see how, these rules in isolation might be kind of confusing, but if you draw it out, it's really easy to derive them. So going to the probability of A and B rules, probability of A and B is equal to the probability of A times the probability of B given A, which is equal to the probability of B times the probability of A given B. But there's a special case, which is when A and B are independent, and this is an important concept in machine learning, independence of probabilities. If A and B are independent, then it's just probability of A and B is equal to probability of A times the probability of B. We make the independence assumption in machine learning all the time, where we assume that each data point is independent of every other data point. It's a reasonable assumption in most cases. So we'll intuit this rule in a second, but let me give you one last probability rule, and then we'll move on to other probabilistic concepts, which is called Bayes' rule, which is that the probability of A given B is equal to the probability of A and B divided by the probability of B. And a nice way to intuit Bayes' rule is, again, to draw it out. So we have our event space, and we have B, and we don't really care about A except for where it intersects. So this circle is A, this circle is B. So if we're saying probability of A given B, the given B tells us that we're only considering the B circle. So everything we care about is not the event space, the total possibilities of events. Now it's just B. We've constrained it to B, so we're saying given B. So the probability of A and B, which is the intersection there, is the portion of the circle of A given B is the portion of the circle where A and B intersect, and B divided by B, which is the total space we're considering when we say given B. Does that kind of make sense? Right. So again, drawing it out makes it really clear, I think. And so just sneak peek to naive Bayes, and we'll have a whole class on this later, pretty soon actually. But in naive Bayes classification, which is a non-parametric classification method, meaning that we don't learn parameters, i.e. we don't use gradient descent in naive Bayes. We simply model probabilities. And we model, in particular, the probability of our output given our data, which according to Bayes' rule is that equation. And so we're modeling the probability of each output class given the data values. And in naive Bayes classification, you simply predict the class with the highest probability. So we'll cover it in more detail, go through some examples, but here's a sneak peek of how probability is directly used for one type of classification. And that's actually pretty intuitive. Like, what's the probability of this class given the data? It's kind of a very intuitive method. Not that linear and logistic regression are not very intuitive as well. Yes?
So can we think about it as the finding, I guess, the predicted values given a training data set?
Yes, yeah. So you would model it on the training data set, and then you would predict using new test data in the same way. So it's all these methods you split into train and test. So the train test split stuff is going to apply for every supervised method that we learn. Yeah.
What does a y represent in the right side of the equation? Because we are trying to find y, I think. Is it y hat or is it y?
Well, this will be more clear when we go to the base class. Okay. So that's probability rules. I now want to talk about probability distributions. So we'll come back to all this naive Bayes stuff. That was really just a sneak peek to get y'all excited about why we're using probabilities. Did that get y'all excited? No. Okay, some people, good. In probability classes, did y'all learn about probability distributions like the normal distribution? What about like Bernoulli and hypergeometric? Okay, cool. Okay, let's just review it really quick. I think y'all know the concepts, but we'll just quickly review these. So we'll start with the normal distribution. Normal distribution, which is also popularly referred to as a bell curve. And if we draw out the normal distribution, you'll probably know or recognize it. It often looks like that. That look familiar? Bell curve, cool. We have certain properties of the bell curve or normal distribution. We have its mean, which is right in the center, and it's convention to call that mu, so that U-looking symbol. And they also have a standard deviation. And so these are the parameters of this model. And so, I've drawn an example where, let's say mu, just giving it an arbitrary value, 0, and standard deviation 0 point that value. But we can change these parameters. And the distribution is still normal, but it changes a bit. So that's also a normal distribution, but with different parameters. We could shift mu, the mean, and it would be the same distribution, but shifted left or shifted right.
What is the function for the normal distribution?
Yeah, we're getting there. So we're in fact getting there now. So the function for this equation, for this distribution, is super ugly, and please don't memorize it for this class. You can memorize it for other classes or if you're curious. But this is like where I feel like I'm going to start bogging y'all down with math. So we're just going to do it today, and let me know if y'all like it, because we're going to end up deriving mean squared error right now using this, which is going to be cool. You're going to see why do we actually use mean square error from a mathematical perspective, but maybe y'all are like, I just prefer it when you give me the intuition. So just let me know what y'all prefer after we go through this, and I can adapt future classes accordingly. So the
What symbol is that by the x? Something of x?
f of x.
Oh, f of x. Okay.
Let me redraw that. Sorry. So
That's not a Greek letter.
yeah. So really ugly equation that kind of doesn't matter, and I was hesitant about doing this with y'all, but I guess to have a thorough machine learning class, we have to do it. I won't quiz y'all on this or anything. So this is the equation for a normal distribution. Isn't that an ugly equation? This is the equation that gives us the bell curve. So let me just, for those who are looking at the notes, clarify that this is an ugly equation and there is no need to memorize. I mean, there's no need to memorize anything really because the exams are open notes. But so that's the equation, and x is the input, and mu and sigma are the parameters of that equation. And this equation has a name. This represents the probability density function. Probability density function, or popularly called PDFs. Maybe let me redraw the arrow, or just not draw an arrow to make it clear it's that whole equation. And what probability density functions allow us to do is to calculate probabilities. So for example, let's say that we have a probability density function. I'm just going to draw one like that. And let's say that this x value is 3 and this x value is 5. Then the probability that x is between 3 and 5 is equal to the area under the curve between 3 and 5. And this is the other part of calculus. That's the integral from 3 to 5 of that ugly equation with respect to x. So equals the area under the curve of the PDF from x equals 3 to x equals 5. Don't worry about the integral signal. We're not really going to use that too much in the class. But just to be thorough, that's technically the integral from 3 to 5 of that probability density function. That tells us the probability that x is between 3 and 5. We'll come back to the normal equation PDF in a second, but I want to cover just one more distribution, and then we'll get to deriving mean square error. Any questions, though, on the normal equation? Not normal equation, normal distribution.
So are we going to take the integral?
No, you don't. Not in this class.
Okay.
But you would if you ever wanted to calculate a probability of something between, let's say it's common to have bell curves for exam grades, and you wanted to know probability that someone's exam grade is between 90 and a 98. Then you would look at the area under the curve from x equals 90 to x equals 98. And you might get, what would be a good value for that? Like 90%? I don't know. So that's what you would need.
So you would need that if you would evaluate, but we're not going to do any evaluation?
Exactly.
Okay.
I'm just building up intuition on what the normal curve PDF is, because we will use that for our derivation. But it's not like this derivation is going to be something you'll be quizzed on, but it's kind of cool to see. So another distribution is the Bernoulli distribution, and this is a discrete distribution. So normal distribution is used for continuous variables. What's the probability that a variable has a value between these two values? Bernoulli distribution you could basically think of it as the probability of flipping a coin with probability of heads P. And when we have discrete distributions, we don't call it probability density functions. We call it probability mass functions. Not going to be tested on this. And it's not going to come up in homeworks either. But for the Bernoulli distribution, the PMF is pretty intuitive, actually. So this equation's nice. This equation we can understand. It's P if, let me just write if heads, and it's 1 minus P if tails. And another way to write this, when you repeatedly repeatedly do some coin tosses, and this way of writing it's even more intuitive, I think. For repeated coin tosses, can be written as the probability of heads times the number of, or to the number of heads power, times the probability of not heads, 1 minus P, using the probability rules, to the power of 1 minus, to the probability of 1 minus 0 if y is 0. And basically what, I think this equation's really clear with an example. So just an example, if we're flipping, if we wanted to know what's the probability of heads, tails, when flipping a coin with 60% probability of heads, then that would simply be probability of heads times the probability of heads times the probability of tails times the probability of heads times the probability of tails, which can be rewritten as probability of heads to the third power times the probability of tails squared. So hopefully that example makes the equation pretty intuitive. Each coin flip is independent. It's kind of a nice review of probability and statistics, but I'm not going to quiz you on that. But one reason I wanted to cover these distributions is to motivate a technique called maximum, maybe signify it's a new section, maximum likelihood estimation. Often abbreviated as MLE. And so maximum likelihood estimation is building up on a concept of likelihood, which is probably new. I don't know if likelihood is really covered in intro probability stats, but likelihood's actually pretty intuitive. So let's just cover that. Likelihood basically comes up in situations where you want to know the likelihood of the parameters to a model. For example, that would be likelihood of mu and sigma for that normal distribution given the data. So that's how we write that, and we can think of it as the likelihood of the model parameters given the data. And so, for example, if we have data that look like this, in one dimension, you could have many normal distributions that fit the data. Perhaps a normal distribution that fits the data well. Oh, didn't start that off well. Might look like that. Maybe a bad distribution that doesn't fit the data well might look like that. Another example of a bad distribution that doesn't fit the data well might look like that. So what we wanted, well, let me write this out. So this, that, and that are different basically parameterizations of the normal distribution. And so just to be clear, i.e. are different mu and sigma values.
That's maximum likelihood?
This is just likelihood right now. This is so, here this is just parameterizations of the model.
What's it a model of?
It's a model of the normal, it's the normal distribution.
Oh,
So
okay.
our model is the normal distribution in this example. And what we want to do in maximum likelihood is to maximize the likelihood that our model parameters take a certain value given the data that we have. So ideally, we'd get something that looks like the red distribution for these data rather than the green distribution or the purple distribution. And so before we get there, though, let's just think about likelihood now for many independent data points. So a big assumption in machine learning, as I said before, is that all the data points are independent. So assuming each data point is independent from each other, which is the usual case, then the likelihood of our model parameters given a bunch of data points, x1 through xn, is going to be the value of the PDF or PMF, depending on if it's a discrete or continuous distribution, multiplied out for each data point. And the intuition behind why this is that if you have, basically the likelihood is proportional to, you could think of it as proportional to the probability that you would have, you would get the distribution values that you have. So like, for example, if you have, let me draw it out here. For example, if your data point has this value, then the likelihood that you have this distribution is higher than this distribution because the value of the PDF is much higher. So so is that kind of an intuitive explanation as to why we the likelihood is at least proportional to multiplying out the values of the PDF? Okay, so that's just likelihood of a bunch of data. We're not maximizing anything yet. Important computer science problem that's probably come up in other CS classes for you. If
I have a question.
Yeah.
Over here, does data include both U and sigma?
Yeah, exactly. I'm using theta as a set notation, so it's a set of mu and theta.
Think about
Mu and
the
sigma.
plot a little above where you had these bunch of data points.
Mhm.
Are you assuming each data point as potential U, or can we just fix, like if we have a range of data points, can we fix U anywhere?
So the distribution represents the distribution for all the data points. So you don't have a different mu or sigma for each data point. You get the mu or sigma from all the data collectively. It's the distribution of the data, or what's the bell curve of the data for a normal equation. So a practical consideration, but this will come up in naive Bayes and probably in some of your other classes. If you have many data points, then multiplying fractions repeatedly will underflow. So for example, 0.001 times 0.001 times, and do that. Let's say I have a data set of 100,000. That's going to be 0.00000, like more than 100,000 zeros, 1. And computers can't represent that. So what we do in a bunch of machine learning applications is take the log. Therefore, we take the log and of the likelihood. And let's recall an algebra rule that the log of A times B is equal to the log of A plus the log of B. So the log of our likelihood is equal to the log of the likelihood of x1 for x1 plus dot 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 plus log of likelihood for xn. And now that we're summing, we're much less likely to overflow or underflow. And the reason we can take the log, and this is kind of a recurring theme in math in general, but that the log of any function increases and decreases the same as the function. So if the original function increases, then the log of it will increase. If the original function decreases, the log of it will decrease, which is really convenient because now, let me just give you the rule of maximum likelihood estimation. So in maximum likelihood estimation, we go back to that calculus optimization procedure that we have seen a few times now. We set the derivative of our likelihood to 0. Sorry, with respect to parameters equal to 0. And then we solve for our parameter values. That's maximum likelihood estimation. It's kind of the same as any optimization procedure. So this is just a regular optimization problem like we've seen before in this class when we covered calculus. Regular calculus optimization problem where, again, you set the derivative equal to 0, and that'll tell you where the slope of the tangent line doesn't change, and therefore it's local minimum or maximum, and we find the high points of those, so the maximum. And so when we solve for theta, that will give us the values of theta, which maximize the likelihood that we get those parameters given the data, and therefore those values of theta are probably the best parameterizations of the model. So really this is a general paradigm of doing machine learning where you want to find the parameters to your model that maximize the likelihood. So if you model the likelihood and you maximize it using calculus and solve for your variable that you're differentiating with respect to, which is the model parameter, and you solve for those model parameters, then you get the optimal value for those parameters. So that's kind of a lot. I'm not going to test you thoroughly on this, but any questions just from an intuitive standpoint? And when I say thoroughly, I mean at all, but it's still good stuff to know. Any questions though? Okay. I think it's really cool, but I know it's kind of a lot all at once. So sneak peek for beginning of next class. And you can let me know if you want me to derive this next class or not. But the big takeaway for linear regression that we can derive next class if you want, but we can also not do it, is that maximizing the likelihood of linear regression is equal to minimizing the mean squared error for linear regression. And that's the mathematical reason that mean square error is a nice loss function, because minimizing mean square error is the same as maximizing the likelihood of the parameters of the model for linear regression. So kind of cool stuff. Let me know at the beginning of next class if you want me to show you how that works. And otherwise, we will move on. But we could also use this to derive the loss function for logistic regression. So I do want to show you that as well. So see y'all on Thursday.